Okay, perfect. Yeah, so we were talking about rolling without slip. And what we will do now is sort of review it a little bit and then build on it to build some intuition about it. So what we were doing last time, so like I said, this is kind of a super important topic in terms of its application to engineering. Um, and we consider the simplest case where we have a circular object rolling on a flat object, right? So, and then we said we have point G on the circular object, which is the center, point P on the circular object. So P is the point on, let's say, wheel that is currently in contact with ground, and G is the center, and R is the radius of the object. And then we said, imagine that this thing has velocity v naught and angular velocity omega, or vg, let's say. Okay, and we have I as usual and j, like so. And this is center of disk, center of wheel. And we said rolling without slip implies Vp equal to 0, okay? So velocity, point in contact with the ground, has 0 velocity. Okay, so that's what we mean. And then slip, when we say slip, we basically mean Vp, okay? So if not equal to 0. Okay, so and then we derived an expression relating omega, the angular velocity, and the linear velocity Vg, such that velocity of the contact point equals 0. So relation between Vg and omega that ensures Vp equal to 0. Okay, so this is sort of what we did at the very end of last lecture. So Vp equal to 0 is where we start with. And then we can write Vp as Vg plus omega cross Rp with respect to G. And Vg is, well, this is equal to 0, the left-hand side. And then Vg is Vgi, because, well, we assume that it's going to the right with some velocity Vg, a scalar. And omega is, vector omega is the scalar omega times k, cross Rp with respect to G. Well, this point relative to this point is this vector going from G to P, which is R times minus J. So it's minus Rj. And we can expand this out. So Vgi plus or minus R omega k cross J. And k cross J is minus I. So what we have is Vg plus R omega I. Okay. So basically, well, let's actually, we can leave the 0 out for now. So VP is going to be equal to VG plus R omega I. Okay. So let's see if I can pull this picture here. So VG is moving in this direction, and omega is this way. So the velocity of this point is going to be this velocity plus a contribution due to omega, so which is going to be R omega. So VG plus R omega, so because omega will sort of try to turn P relative to G in this direction. So VG plus R omega is basically going to be VP, okay? So VP is VG plus R omega. But if you want VP equal to 0, so if VP equal to 0, namely rolling without slip, then what we have is VG equals minus R omega. Okay, so what does that mean? Well, VG is moving, G is moving with some velocity, and then omega is just the right magnitude so that what you're adding due to omega to this point exactly cancels out VG so that this point is momentarily at rest at every point in time. Okay, so this will I guess I'll just leave it at that. Okay. Any questions about this? So that's what we mean by rolling without slip. The contact point is momentarily at rest. So let's do the acceleration version of this. So relation for accelerations. So imagine for a moment that we have, let's say, AG in this direction as well, and alpha in this direction. So this is alpha K. This is, if you want to write it in terms of vectors, this is AGI. So what is the relationship between AG and alpha? So it turns out we cannot assume that AP equal to 0, even though VP equal to 0, okay? So relationship between AG and alpha is obtained by differentiating basically the relationship between VG and omega. So we just showed VG equals minus R omega, and then you differentiate both sides. You get AG equals minus R d omega by dt, which is alpha. So AG equals minus R alpha. Okay, so that's the relationship between the acceleration, the linear acceleration of this point and the angular acceleration of this disk or wheel, assuming that the thing is rolling without slip, okay? So any questions about that? And then I sort of snuck in a sentence here, it turns out we cannot assume AP equal to 0, even though VP equal to 0. And it turns out that we can compute the velocity acceleration of the point P, and it's not equal to 0. So we can do that. So what is the acceleration of P if not 0? So we can compute it using the standard formula that we have. AP equals, well, AG plus alpha cross R P with respect to G plus or minus omega square RP with respect to G. So we can do that. You can compute that, and that's basically it's going to be equal to AGI plus alpha K cross RP with respect to G. We showed that it was minus RJ, right? So it's RP with respect to G is this thing is R in the negative J direction. And then minus omega square minus RJ. Okay. So let's expand this thing out. AGI minus R alpha K cross J minus omega square or plus omega R omega square J. And K cross J is minus I. So AGI minus R alpha minus I plus R omega square J. I'm just sort of working this out in long form. Okay, so that's the acceleration of point P given the acceleration of G and the angular acceleration, the linear angular velocity. And we already know if the thing is rolling without slip, AG equals minus R alpha. So equals 0I plus R omega squared J, because AG equals minus R alpha for rolling without slip. So basically R omega squared J. Okay, so AP, so the acceleration of the bottommost point, is R omega square in the J direction. So it's basically in the upward direction. Okay, this point moves to the right, accelerates to the right. This point is momentarily at rest, but is accelerating upward at every point in time. Okay. So it's basically like a centripetal acceleration, if you want to think of it like that, related to a centripetal acceleration. And someone, maybe Daniel, asked, okay, how does this point P, if it is at every point in time at zero velocity, well, how does this thing get off the ground at all, right? So we are saying this object moves in a manner that the contact point is at rest at any point in time. But if the contact point is at rest, well, how does it become not the contact point? Because as it's rolling, the contact point keeps changing, right? Right. So initially, this is the contact point. After a while, this is the contact point, and so on. Right. The contact point keeps changing as the thing rolls forward. So how does it get off the ground if the velocity is zero? The idea, the intuition kind of, is that the acceleration is not equal to zero of that point, and the acceleration of that point is upward. So that acceleration basically pulls it upward, so to speak. So that's the resolution of the paradox, more or less.
So, Professor, can I just like clarify for that for myself?
Yes, absolutely, yeah.
So because the point P is the point that's on the bottom, its motion is limited to the I vector, and since its acceleration is only in the J vector, it doesn't have any. Does that kind of also resolve that paradox?
Say that again. Its motion.
So its motion, since it's always at the bottom of the circle, its motion is only in the I direction. But since its acceleration is in the J direction, it's not. It doesn't. That's not really a contradiction then.
I suppose so. Yeah, that's right. Yeah. So this is the acceleration that quote unquote pulls the point P up off the ground. Okay. So let's actually try to understand a little bit more the velocity distribution on this object. So if I draw a big picture here, okay, let's just ignore that imperfection there. So we have a point P there. So this point itself has, this point itself has zero velocity. Now, what is, and then this point has velocity VGI, like so. Okay, so this point has VP equal to zero. What about this point? What is the velocity of that point? Can you think of it?
It should have the same I velocity, but I think it should also have a J velocity.
Sorry, I couldn't hear that very well. Say it again, sorry.
It should have the same I velocity as the center point, but and also have additional J velocity, which I don't know what the formula for is.
Yeah. The fact that you're saying that there's a J velocity is exactly right. The I velocity is actually going to be slightly different, I think. But let's see sort of how to work that out. So basically, we talked about this thing called instantaneous center of rotation. I guess last lecture or the lecture before, perhaps. And for this object, what is the instantaneous center of rotation? Now that we have sort of talked about rolling without slip, if this object is rolling without slip, what is the instantaneous center of rotation?
P.
It's the point P. Okay, so this is going to be instantaneous. It's as if the whole object is rotating about that point instantaneously, but that point sort of keeps changing and moving forward. But momentarily, the whole thing is rotating about that point. But it's not rotating about that point forever. Like, it's not a pure rotation about that point, but at the moment it's rotating about that point. That point has zero velocity. Okay, so given that that's the case, so this is because VP equal to zero. If you take basically this vector or this line, then the velocity of this point is basically going to be perpendicular to that line joining, and it's going to be basically omega times that distance, whatever that is. Okay. Um, so etc. So, and then if you say, what is this point? It's going to be, what is the velocity of this point going to be? Any guesses? This we can say immediately what it's going to be.
2 VA.
2 VG, that's right, 2 VG.
Okay.
Yeah, but I think you got the idea right. But basically, this is going to be 2 VG, because VG is basically R times omega. So VG is going to be does that make sense why this is 2 VG? So VG, if this is R and you have some omega, VG is going to be R times omega with the negative sign. And this point is going to be 2R times that same omega.
So does that mean the point on the right's magnitude is radical 2 times VG?
That's times R, that's right. Yeah, radical 2 times VG, that's right, yeah. It's going to scale with this distance, that's exactly right. This is square root of 2 times R, that's right, okay? So we can sort of do this more slowly. So I guess we can sort of write that down for now in this direction, I suppose. Equals, let's call this point A or something. I don't know, BA absolute value, I guess. This is G, this is B, etc. So let's actually do this more slowly. So we just said VB equals VP plus. So let's say we want to derive the velocity of this point. Let me actually write this here so that on the right-hand side so that things are clearer. Okay, so VP is 0. And then we have VG equals minus R omega. Okay. What is VB? You can say VB equals VP plus omega K crossed with R B with respect to P, which is 0 because VP is 0, plus I'm going to substitute for omega VG over minus R, if you will. And then RB with respect to P is basically 2RJ. Okay, so the R gets canceled. So, and then K cross J is minus I. So we get minus VG K cross J equals times 2. So we have minus 2 VG minus I, or 2 VGI. Okay, so that's how we get VB equals 2 VG. And similarly, VA, we can do that here. Let me do that here. VA is again VP plus omega K crossed with R A with respect to P. VP is 0. And omega we've established is minus VG divided by R K. And then crossed, well, this is R, this is R. So that vector from P to A is Ri plus Rj. So that's basically Ri plus Rj is that vector. And we can multiply this through, the R's get canceled. And we got minus VG, K cross I, minus VG, K cross J. Let me write in a different color, I guess. And then my K cross I is j. So we have minus vgj, and then we have plus vgi because k cross j is minus I. So that's what you get. So that's, if you have a point A, it's got basically um, um, its x component is vg, its y component is vg. So whoever said the x component of it is vg for originally was exactly right. So yeah, so that's basically vg, and then if you want the absolute value of vg, va, then it's going to be square root of 2 vg. Okay, this is just equal to vg square plus vg square. So this point is going at a 45-degree angle, um, and has equal values for VG, equal values of the X and Y components. What about this point? So this point is going to have velocity like in the 45-degree direction this way, because again, it's sort of rotating about this point momentarily, and so on and so forth. It's going to be basically VGI plus VGJ. So any questions about this? So if you take this, circle and say this is the contact point, and then you sort of draw a line to any point really, then basically if that point has some velocity, every other point will have velocity like that. And so on, right? So if you have some other point, so different points have different, so these points are traveling like this, right? So the points along this line are sort of going in this direction with increasing velocity as you go out. The point along this line have basically velocity horizontal, and have increasing velocity as you go out. And then the points on this line have velocities in this direction and increasing velocity as you go out. Any questions about this? So that's what we mean by rolling without slip. So velocity of different points on the wheel can be understood by thinking that the wheel at the moment is rotating about P, okay? So that's the idea of instantaneous center of rotation. But, super important point, but accelerations do not obey this, do not obey. So the instantaneous center of rotation is a concept for velocities. It's not for accelerations, okay? Do not behave like pure rotations about P, only velocities So for accelerations, you just need to use the acceleration formula. Well, even for velocities, we sort of just use the velocity formula, but at least you can at least get intuition for what the velocities are going to be for different points. For accelerations, just use the formula. A whatever point, AQ equals AP plus alpha cross RQ with respect to P minus omega square RQ with respect to P. Okay, so you just use that formula. Any questions? Okay, so we already saw the velocity of the bottommost point, AP. AP has upward, sorry, not velocity, acceleration of the bottommost point, which is R omega squared J. So it's an acceleration in the upward direction. Can we find the acceleration of, let's say, a point A or point B or something? Let's try to find the acceleration of point A or point B, let's say. So exercise. What is AB? The topmost point. Okay. How do we find this? So we can find it basically the same way using this formula. For all these questions, you just go back to this formula. So we just now do AB. So just to recall the picture, we have that, and we have AG, P, B, VG of that point. We have omega, we have alpha, and then we have AG plus R alpha equal to 0, VG plus R omega equal to 0. This is no slip. When we say no slip or rolling without slip, it's the same thing. Okay, so AB is given by AG plus alpha K cross R B with respect to G minus omega square RB with respect to G. So G is a point that we know the acceleration for. Its acceleration is horizontal and is given, let's say. So we can plug everything in. This is AGI. Alpha, your alpha is basically AG divided by minus R. So if you want to use that. And then RB with respect to G is RJ, right? So this is G, this is B, it's RJ minus omega square RJ. And then all we have is a little bit of simplification to do. So AGI minus AG divided by R gets canceled. K cross J minus R omega square J. K cross J is minus I. So we have AGI plus AGI, because this minus and this minus becomes a plus, and then minus omega square R J. So this is actually 2 AGI minus omega square RJ. Okay, that's kind of interesting. So this point has no horizontal acceleration, only a vertical toward the center acceleration. This point has only horizontal acceleration. This point, we just said, has twice the horizontal acceleration of this point, and then has basically the centripetal acceleration downward. Okay, exactly the same as before, but in the towards g now. Okay, so if you want to plot the acceleration pictures, then you would do this. And this point has both 2agi and r omega squared j with the negative sign, I guess. And these points will have other velocities, okay? Any questions? So, like, what's the moral of the story, so to speak? It's that when you have this object rolling without slip about this point, different points on this wheel have different velocities. And the velocities behave as if they're rotating about this point. And then different points on the disk have different accelerations, right? So if you are sitting, let's say, somewhere on this wheel, and if you're sitting at the center, then and the thing is accelerating, you would just experience a constant acceleration to the right. But if you're sitting on the edge for some reason, then as you get here, you are going at twice the acceleration, and you're also pulled toward the center. And then when you're here, it's going to be something else, I suppose. And then when you're here, you have the lowest possible acceleration, and it's entirely toward the center. Any questions? So that's rolling without slip, at least for the simple disk. You can sort of generalize rolling without slip, more general rolling without slip. So if you have two objects, let's say if you have two objects, and let me draw another object in a different color. And they are moving in some manner, for some reason why. So this is point P1, and this is point P2. Two objects contact at P1 and P2, contact each other, I guess, touch each other, contact each other. Respectively on the two objects. So when I say P1 is basically in this object, P2 is on this object. So maybe I should make this P2 green or something. But basically P1 on object 1. P2 on object 2. And this object can roll without slip on this object, basically sort of in a nice smooth way. And the condition for rolling without slip is is basically that VP1 equals VP2. In other words, these two contact points have no relative velocity. So contact points have no relative velocity. Any questions about that? So imagine this thing rotating in some manner, but for instance, this rotates, maybe this also rotates, but if they rotate in a manner that they are in contact and the velocities match basically as this thing rolls on the other thing, that's basically called rolling without slip, more generally, okay? Let's do an example. So pulleys. So this is the simplest example, perhaps, where you have so this now is like the disk. This now is like the ground. Like this belt is like the ground. This belt is like another ground, kind of. Let's say pulley belt has no slip on the pulley. So they'll say this is A, this is B, and VB is, let's say, 1 meter per second. VA equals 1 meter per second. And the pulley itself has some angular velocity omega. So given VA downward and VB upward equals 1 meter per second, what is omega if our pulley equals, let's say, 0.3 meters. Okay. So what is that going to be? So this is belt has no slip, or you can think of pulley rolling without slip on belts. Okay, so if you think of this pulley, let's say this is the center point of this pulley, and let's say this point is C, this point is D, and this point C, well, this is the pulley, right? So this is pulley. VG now is equal to 0 because the pulley is not going anywhere, not moving, let's say. G not moving, let's say. Not well, pulley is kind of moving, but G not moving. And then this point C is kind of attached to point B, which has got some velocity. Okay, this point D is attached to point A, which has velocity 1 meter per second. So rolling without slip means that the velocity of point C on the pulley needs to be exactly the same as the velocity of point B on this belt. So this belt is inextensible, which means that the velocity of this point is the same as the velocity of all these points until the point that just touches C. So So let me erase this a little bit. Same velocity until the point that touches C. So for no slip, we need VC equals 1J. So C on pulley, right? Okay, so C is a point on the pulley, and there is this belt. This point on the belt is moving at 1 meter per second, and every point on this belt will move at 1 meter per second because it's not changing length, it's not extensible. And therefore, this point to not have slip with the point on the belt that is just adjacent to it needs to have the same velocity as the belt, which is 1 meter per second, right? So VC equals 1J, and VD, this point needs to have minus 1J, okay? So we now know the velocity of G, we know the velocity of C, we know the velocity of D. Well, what is omega? So VG equals 0, VC equals VG plus omega K crossed with Ri, basically. So this is going to be R G with respect to C with respect to G. Okay, we're just using the standard formula here. So this is 1J equals 0 plus omega K. We said R is 0.3 or something. K cross I is J. So 0.3 omega equals 1, or omega equals 1 over 0.3 radians per second. Which I suppose was relatively intuitive, perhaps, at the beginning itself. But if you are sort of doing a more complicated problem, you would just set things up using these equations carefully and then derive omega like this. Was that clear? Any questions about that? So let me give sort of another problem, and then I guess I will just stop there. So exercise is, imagine, for instance, you have this pulley and you're pulling this up, and VB equals, let's say, 3 meters per second. VA equals 2 meters per second. Okay, so no slip. Determine VG and omega, where this point is G. Okay, so I guess that's the question. So imagine, for instance, it's being pulled up in a manner that this side is going at some speed, this side is going at some other speed, which would necessarily mean that this whole point, this thing is moving up and is also rotating, right? So we do have VG, and then we do have omega, and the VG and omega are contriving in a manner that basically this point is moving at 3 meters per second and this point is moving at 2 meters per second. And that's possible, even though it sounds weird. So I'll leave that as an exercise, and then I'll probably post the solutions here, and then for next class we will move on to something else. I guess I'll stop there, and then see if people have any